This is the solution video for AP Physics Suggested Problem Set 3.2. So starting with a conceptual question where we have a clothesline that hangs between two poles. So two poles, we have a clothesline in between them. Now, no matter how tightly we stretch this line, it's got to sag some amount at the center. Why is that? Well, we know that gravity is acting on this line at all points. So if I actually go and make a free body diagram for the very center of this line, what we have is we have a force acting downward, that is the force of gravity, and then we have two other forces that are acting somehow to the left and right, because we have tension in the line. Now the reason that it has to sag some amount, so we have some amount of sag here, the reason it has to sag to some degree is because if this were completely flat, then we would have a situation where tension cancels each other out, sure, but there's no way to cancel the force of gravity. There is no force. There's no force to cancel out the force of gravity. Therefore, the line should be accelerating. If there's nothing to cancel out the force of gravity. So there must be some way to cancel out the force of gravity for this line to not move. That comes from the fact that there must be some amount of sagging, meaning that there's some angle that these tensions make with the horizontal so that there is a way to cancel out the force of gravity by taking their components that act in the vertical direction. Question 5.6 involves a wrecking ball that is held in place by two light cables. That means that there is no mass to these cables. The mass of the wrecking ball, M, is 3620, and we want to find the tension B that the cable makes and tension A in the horizontal cable. So we'll start by sketching a free body diagram for this. So I have three forces. I have acting downward, a force of gravity, acting up and to the right, tension B, and then straight left, tension A. So I will go ahead and sketch my axes here so that I can define my angle. So if this angle here that tension B makes with the vertical is 40 degrees, then that means that this angle right here is 40 degrees by opposite interior angles, if you want to know. So what do we do from here? Well, we have a free body diagram, so I can split this up into two components for tension B. So I have this component acting horizontally and this component acting vertically. So I can go ahead and just skip a couple steps by saying this is TB and it's the side opposite the 40 degrees, so that would be TB sine 40. And then this would be TB cosine 40. So I'm going to take this and I'm going to create some sum of force equations. So in the x direction, I have TB sine 40 minus TA equals MAX, which is 0 because we are just sitting here. In the y direction, I'm going to leave a little space. In the y direction, I have TB cosine 40 minus FG, which is equal to MA in the y direction, which is also 0, as we're just sitting here. So I have a couple things that I can do. Firstly, I want to find tension B. So since I know M as 3620 kilograms, I can use my y equation and just solve for tension B. So I have tension B cosine 40 minus FG equals 0. So I can replace the fact that FG is equal to mg in my equation. So I have tension B cosine of 40 degrees minus mg equals 0. And continuing the same train of thought here, tension B cosine 40 would be equal to mg, or tension B is equal to mg over the cosine of 40 degrees. So now I can just substitute some values. So I have 3620 kilograms times, I have a calculator, so I'll just use 9.8. And I need to use it anyway for cosine 40, so I'll just go ahead and use 9.8. So cosine of 40 degrees. So I plug all this into my calculator. And I get a tension of 46,300 and we'll say 11. And that's going to be in newtons. So this is part A that came after all of this setup. Now part B, I'm going to do over here, is just to find tension A in the horizontal cable. So now that I know tension B, I can use my x direction equation and say, all right, tension B sine 40 minus tension A equals 0. Therefore, tension A is just going to be tension B times the sine of 40 degrees. So substitute in my value here, and I have 46,311 times the sine of 40 degrees gives me 29,768, we'll say. And that's also newtons. So a quick check to make sure all of this makes sense. So the weight is going to be approximately 36,000 newtons, and tension B is going to have a larger force than the weight that it's supporting, because not only is it supporting all of the weight, it is also pulling to the right to some degree in order to cancel out tension A. So tension B will be larger than the force of gravity. So this does make sense. Question 5.7 has now a symbolic problem where we have some object, which is a work light, that is hanging from a couple of cords. So let's start with a free body diagram for each. So for object in A, or for the setup in A, we have three cords. We have A, B, and C. So pulling downward, let me go ahead and do that again. So pulling downward, we have tension C. Pulling up is tension B. And pulling up, up right is tension B. And then pulling up left is tension A. So I need to define some angles here, so I'm going to sketch some really light axes to define my angles. And we see that tension B is 45 degrees with this horizontal, so we'll say this is also 45 degrees by opposite interior. Same thing with the 30 here, so this is 30 degrees to the horizontal. So we also have a situation where we want to just draw right at this point where the mass is connected. So we have a free body for just that little point where we have pulling downward, weight, and pulling upward, tension C, for completeness sake. So now we're going to do the same thing for this other object. So we're going to do a free body diagram where we have tension C pulling down, straight down. So this is this point. Tension C pulling straight down. Again, tension B up and to the right. And we'll define the angle in a second. And tension A is actually down and to the left. So I'm going to sketch my axes here. And so tension B is 45 degrees above the horizontal again. Tension A, so this is defined as 60 degrees to the vertical. So what I can do is I can actually just find my 60 degrees right here. I don't have to do any extra math, just by opposite interior. So here are my two free body diagrams for the points. And what I want to do now is actually go and, well, actually I want to draw the same thing over here, right? So I can say that on the right-hand side, we also have weight acting down and tension C acting up, just to make sure we know that tension C is equal to weight. So we'll start with that bit, right? Sum of forces in the y direction right here is just tension C minus W equals MAY, which is 0. So I can just say that tension C is equal to W. I can do the same thing for the other drawing. So in the y direction, tension C minus W equals MAY, which is 0, so tension C is equal to W. Now, I want to set up some equations. So for the left-hand one, so keep in mind what we're looking for here. We're finding the tension in each chord. So tension C is done. It's just weight. In both cases, it's just weight. So now I want to go and look for part A at how my equations are set up. So for this top free body diagram, sum of forces in the x direction is going to be tension B times the cosine of 45 degrees. Let's scroll a little that way. Minus tension A times the cosine of 30 degrees equals MA in the x, which is 0. In the y direction, I have a few things here. So I have tension A times the sine of 30 degrees plus tension B times the sine of 45 degrees minus tension C equals MAY, which is 0. So I have my system of equations here, and I know that tension C is equal to W. So I really have no way to simplify this, unfortunately. So I actually have to do this the gross and ugly way. So I'm just going to go ahead and use my x equation to come up with an expression for TA. So solving for TA, actually I'll start for TB first. So solving for TB in this first equation, I'm going to have tension A times the cosine of 30 degrees over the cosine of 45 degrees. And I'm going to substitute that in to my y equation. So that will give me tension A times the sine of 30 degrees plus this whole mess. So it's going to be tension A cosine of 30 over cosine of 45 times the sine of 45. And then we'll say that is equal to TC, which is W. So I'm skipping a few steps for the sake of space. So now I actually can factor out tension A, and I'm actually going to go ahead and do a couple steps at once here. Right? So I'm going to collect all of this trig and then divide by it. So I have sine of 30 degrees plus cosine of 30 degrees, and then I have sine over cosine, so I have tangent of 45 degrees, which is nice because that's actually 1. So this is all in my denominator. So what does that give us? Well, it tells us that tension A is going to be 0.73 W. And then I can take this and plug it right back in up there for TB. So even though this is a very messy looking situation, if I plug it in up there, so I would have tension B, which is 0.73 W times the cosine of 30 over cosine of 45. My tension B, once I go back into the calculator, is I guess we'll round it, 0.90 W. So there are all three for the green situation. Now we have to do the same thing for the blue situation. So this is really just to practice doing some drills. So starting with the free body diagram here, I'm going to write my sum of forces equations. So I have in the x direction, tension B times the cosine of 45 degrees minus tension A. Now, the way I've defined this 60 degrees is going to be the sine of 60 degrees is equal to MAX, which is 0. And then in the y direction, I guess I'll leave it there. In the y direction, I have tension B times the sine of 45 degrees minus tension A times the cosine of 60 degrees minus tension C is equal to MAY, which is also 0. So we have to go through the same process. First off, I know tension C is W, but I'm going to go ahead and do the same thing I did previously, which was solve for tension B from this x equation first. So doing that, I will have tension B is equal to tension A times the sine of 60 degrees over the cosine of 45 degrees. Then I can take that and plug that into this equation. So that gives me tension A times the sine of 60 degrees over cosine of 45 degrees times the sine of 45 degrees minus tension A times the cosine of 60 degrees equals W. That's my TC. And so again, factoring out my tension A and dividing by what's left over, I have W over sine of 60 times tangent 45 degrees minus cosine of 60 degrees, all in this denominator. So doing that, my tension A turns out to be 2.73 W. I'm going to actually go back and check that in a minute. And what does this tell us? Well, that tells us that tension B, so I plug it back in up here, so that tension B will be the 2.73 W times the sine of 60 over the cosine of 45. Tension B will end up being 3.35 W. Question 5.8 has a car on a ramp that's held by a light cable, so again, no mass, on a smooth, frictionless ramp, so there's no friction. So first I'm going to start by drawing a free body diagram. I'm going to draw it over here so that I have plenty of room. So firstly, I have the weight of the car going straight down. And so we'll say that this is FG, or we can say it's MG. And then we have a cable. And so this is a little interesting because of how this angle is defined. But if I sketch my axes really quickly, I can say that, all right, I have a situation where I'm probably going to rotate these axes because I want to have some kind of line with the ramp later on. So this right here is 25 degrees. And then my cable, my tension force, is actually going to be making an angle of, let's do it this way. Can't make a straight line today. My tension is going to be acting at an angle of 31 degrees above that set of axes. So the other force that I need to concern myself with is the normal force. And so because I sketched these orange axes already, I know my normal force is going to be in line with those. So this is my normal force. And that will actually be defined at an angle of 25 degrees with this right here, right? Because I'm rotating my axes at some point. So the last bit is I'll say that this right here is 25 degrees. Why not just write it everywhere? And that lets me set up my system of equations really well. So that's part A. It's drawing my free body. B says find the tension in the cable. So I'm using my set of orange axes here. So let's be careful. So I have a component of the force of gravity that is going in this direction. Maybe I could use a thicker line. So this is a component of the force of gravity. And there's a component of the force of gravity in this direction as well. So this would be FGY, and this is FGX. So to write my equations, I want to actually go through and use my new set of axes. So this might be, we're going to go slow. So we have a component of the force of tension in the positive x direction, and that is going to be tension force cosine 31 degrees. So actually, there was no reason to rotate axes for this problem, but it's fine. Minus FGX, which is going to be force of gravity times the sine of 25 degrees. And we're just sitting there, so MAX is 0. Then in the y direction, I have normal force. I also have a tension force that is tension times the sine of 31 degrees. And then I have Fg times the cosine of 25 degrees. So I really didn't need to rotate my axes. It was just a little convenient when I was defining angles. So I want to find the tension in the cable. So I can do that just based off of my x direction. So pulling that down, I have force tension is going to be equal to Fg sine 25 over cosine 31. Or I can just go ahead and say that's mg times the sine of 25 over the cosine of 31 degrees. So substituting values here, I have a mass of, I forgot to write this down, a mass of 1130 kilograms. So my force of tension is actually going to be 1130 times, again I'm using a calculator so I'm going to go ahead and use 9.8, times the sine of 25 degrees over the cosine of 31 degrees. So we plug all this into our calculator and we get a tension force of 5.460 rounded, and that's going to be in newtons. So there's my tension force. This all was part B. Now C says how hard does the surface push on the car? So this is just asking us for normal force at this point. Well, we have tension, we have force of gravity, so we can just use our y equation and solve it for normal force. So that's just going to be normal force is equal to Fg sine, try that again, Fg, which I'll actually go ahead and just say is mg, mg times the cosine of 25 degrees minus tension force times the sine of 31 degrees. So my normal force is going to be 1130 times 9.8 times the cosine of 25 degrees minus 5460 times the sine of 31 degrees. So taking this and putting it in a calculator, it gives us a normal force of 7,224 newtons approximately. So because we rotated our axes, luckily, our normal force was easy to solve for. So maybe it was worth rotating in the end. All right, for number 512 here, we have a rocket of initial mass, 125 kilograms, that has an engine that produces a constant vertical force or thrust of 1720 newtons. Inside the rocket is a 15.5 Newton electrical power supply that rests on the floor. So A says, find the initial acceleration of the rocket. So in order to do that, I'm going to start with a free body diagram. So I have the weight of the rocket pulling it down. So Fg equals mg. And then I have some thrusting force that is hopefully larger than the force of gravity. And I'll call that FTH, for force thrust. And this is all I have for my free body diagram. So in the y direction, I have the thrusting force minus, I'll just go ahead and skip to mg, equals ma in the y direction. So I want to find the initial acceleration of the rocket. So I'm looking for ay. So ay in this case, if I solve for it, would be the thrust minus mg all over m. So simply plugging in some values here, we would have the thrust, which is 1720 newtons, minus the 125 kilograms of mass, times, I'm going to be using a calculator, so let's just do 9.8, over the 125 kilograms. So that 125, just a reminder, includes everything inside the rocket. So take out my calculator and put this in, and I find that my acceleration should be 3.96, and that should be in meters per second squared, based off of my SI units. And then B asks, well, when the rocket initially accelerates, how hard does the floor push on the power supply? So I'm going to actually draw a new free body diagram for this, and we'll see what that gives us. So inside the rocket, so actually I'm going to sketch a picture real quick. So inside my rocket, right, this is my rocket. So then I have like a, room inside my rocket that has a power supply. And the power supply is experiencing its own weight. So this is Fg, which is equal to, in this case, 15.5 newtons. And then I have some force pushing up from the floor, which is a normal force. So here, to sum my forces in the y direction, I would have a normal force minus this 15.5 newtons equals ma in the y. Well, because this box is on the rocket that is accelerating 3.96 meters per second squared, then my ay must be identical. So the only difference here is I need to know what the mass of this object is. So because weight is equal to mg, which in this case is 15.5 newtons, my mass is going to be the 15.5 divided by the 9.8 that would be the acceleration due to gravity. So my mass in this case is just going to be 1.58, we'll round it there, kilograms. And so to find this normal force, I'm going to have MAY plus 15.5 newtons. And so that's going to be the 1.58 kilograms of mass for this box times my 3.96 meters per second squared plus 15.5 newtons. So plugging this all into my calculator, I get a normal force of 21.8 newtons. So question 5.14 has three different sleds of different masses that is being pulled across, or that are being pulled across the horizontal ice. So ice here is saying that there's no friction, or actually frictionless is telling us that. And the pull is a magnitude of 190 newtons. So A says find the acceleration of the system. Well, for A, what's going to happen here is the net force is going to be pulling on the total mass for some acceleration. And the acceleration for all three has to be equal to the same thing. So my acceleration is just going to be that net force divided by the total mass. So real quick, we're just going to point out that the net force on this is just going to be the pulling force. Right? There is some normal force on this system, and there is some force of gravity, but that doesn't matter. The only thing we care about is that pulling force. Because in the x direction, which is my net force, all I have is F pull. So my acceleration is just going to be the 190 newtons divided by the total mass, which is going to be 30 plus 20 plus 10, or just a total of 60 kilograms. And so taking this and plugging it in, we have an acceleration of 3.17 meters per second squared. So that's the acceleration of the whole system. Now B says find the tensions in ropes A and B. So the way that we're going to do this is we're going to draw three separate free body diagrams. So I'm going to start with the 10 kilogram boat. So I have force pull, then I have a normal and a gravity, and I don't care about these, but I'm drawing them anyway. And then I have tension A pulling to the left. Then I'm going to do the same thing for the next boat. So I have tension A pulling this boat to the right, and tension B pulling to the left. So I can do my normal and gravity, but I'm not even going to label them. They're not worth it. Then I have, for the last boat, only tension B pulling. So what I can actually say from this is the following. So there's also normal and gravity. So what I can say for this is the following. From the last free body right here, tension B must be equal to the mass that is actually 30 times A. So tension B is actually going to be 30 kilograms times this acceleration that I found in part A, which is 3.17 meters per second squared. So tension B should work out to be 95 newtons. Then, from this second, I can also sum forces in the x direction, and I'll see that I have tension A minus tension B is going to be equal to the 20 kilograms mass times acceleration. So here, tension A is just going to be 20 kilograms times the 3.17 meters per second squared plus the 95 newtons that I just found. So this tension here is going to be 158.3 newtons. So it's all about making sure that you can chain together free body diagrams and know what is going on with tensions. For question 5.16, we have a block of ice released from rest at the top of a 1.5 meter long frictionless ramp. It slides and it reaches a speed of 2.5 meters per second at the bottom. So we need to start with a sketch. So here is some kind of ramp. It is let's actually do this slightly differently. So it is 1.5 meters in length. 1.5 meters in length. And at the top, we have a block of ice that has a mass of 8 kilograms. And V initial is 0, and V final is 2.5 meters per second at the bottom of the ramp. So question A asks, what is the angle between the ramp and the horizontal? So let's use alpha. We haven't used alpha in a while. So we want to figure out what acceleration this block should be experiencing, and then do that as a function of gravity's acceleration. So how do we go about this? Well, first let's find the actual acceleration of the block. So I have V naught, V, distance, and I want to find acceleration. So in order to do that, I'm going to use the third kinematic equation, v squared equals v naught squared plus 2a delta x. So these are all in the x direction. So really I'm just saying that down the ramp is the positive x direction. So I'm going to be solving for acceleration. So acceleration would be v squared minus v naught squared over 2 delta x. So substituting here, and knowing that v initial is 0, I will have 2.5 squared over 2 times 1.5. So the actual acceleration of my block is 2.083 meters per second. So now I want to figure out what fraction of gravity that is. So if I think about this from a free body standpoint, I have a normal force acting this way, I have no friction, and I have a force of gravity acting this way. So what this means is, if my axes are tilted as such, where this angle right here would be alpha, then the only component that is accelerating me is going to be the force of gravity component in this direction. So this is going to be Fg times the sine of alpha. So what that means from a standpoint of net forces is that the sum of forces in this x direction is just going to be Fg times the sine of alpha, which will be equal to m times a. Well, I found a, and so I'm just looking for alpha. So rearranging this, I have alpha is going to be the arc sine of ma over, well, this is mg, so my m's cancel, so it's just the ratio of the acceleration I found to the acceleration due to gravity. So plugging this in, I have the arc sine of 2.083 over 9.8 meters per second squared will cancel out. And so plugging this in, I get an angle of approximately 12.3 degrees. So that's the angle that this ramp is at. And then B says, what would the speed of the ice at the bottom be if there were a constant friction force of 10 newtons parallel to the surface of the ramp? So I already have the angle. The difference here is that I'm going to draw a new free body diagram. So my new free body diagram is going to look very similar. I'm going to have force of gravity acting downward. I'm going to have a normal force up and to the right. And I'm going to have a friction force up and to the left. So what's actually going to change here is only the fact that I now have a different expression for the sum of forces in the x direction. So let's actually say this is A. So the sum of forces in the x direction here is going to be Fg times the sine of alpha minus the force of friction is equal to my new ma in the x direction. So we have a value for the force of friction. It is 10 newtons. So this is equal to 10 newtons. So my acceleration is going to be mg sine alpha minus force of friction all over mass. So I'm going to substitute here. I have 8 kilograms times 9.8 times the sine of 12.3 minus 10 all over 8 kilograms. So plugging this into my calculator, we get an acceleration of now 0.838 meters per second squared. So it makes sense because this is a lower acceleration than before because we have friction slowing us down.